Welcome to the Peacademia course on the basics of semiconductors. This lecture covers IGBTs. Let's start. By the time you finish this lesson, you will learn a brief history of IGBT, differences between IGBT, MOSFET, and BJT, IGBT semiconductor structure, IGBT circuit model, and the IGBT I-V characteristics. The insulated gate bipolar transistor, or IGBT, was invented in the early 1980s by Hans Becke and Carl Whitley as an alternative to bipolar power transistors. The main shortcoming of power BJTs is the low current gain. This low current gain results in a large base current and therefore considerable gate driving losses. Moreover, keeping power BJTs within their safe operating area is a very difficult task to fulfill. Therefore, power BJTs are not a good option even for low power conversion applications. Despite this shortcoming, BJTs are of interest because they possess much higher current density in comparison to MOSFETs. In MOSFETs, only one type of charge carrier is responsible for current conduction. However, in BJTs, both the holes and electrons are responsible for conduction. Therefore, engineers came up with this idea to engineer a new hybrid power switch in such a way that the new device has the advantages of both the MOSFET and BJT. This is the structure of an IGBT. It has three terminals called the emitter, collector, and gate. This structure can be modeled by this electric circuit. Here we have an N-channel MOSFET parallel with an NPN BJT, and there is also a PNP BJT. You may first think that the combination of Q1 and Q2 makes a thyristor. The only difference between this structure and the thyristor in terms of the way the model looks is the N-channel MOSFET. Although this way of imagination looks correct at the first glance, the thyristor operation is strictly prohibited by a high conductive resistor connected between the base and emitter of Q2. Since the conductivity of Rs is large enough, it keeps Q2 in the off state all the time and connects the collector of Q1 to the emitter terminal. As a result, we can come up with a simplified model of the IGBT. In circuit designs, we normally do not use the IGBT model, we rather use its symbol. To turn on the IGBT, we just need to apply a positive voltage greater than the threshold voltage between the gate and source of the MOSFET. Once the MOSFET turns on, the base current of the PNP BJT is provided by the MOSFET and the gate and the IGBT turns on. The IGBT is designed in such a way that most of the current passes through the power BJT and a smaller portion of the current goes through the MOSFET. The main advantage of the IGBT in comparison with the MOSFET is the high current density capability. However, it comes with some disadvantages that make the IGBT improper in low and mid-range power conversion applications. If you look at the simplified model, you'll notice that we cannot apply a negative base current to the power BJT to obtain a faster turn-off time. For turning the IGBT off, all we can do is to turn off the MOSFET, so the base current gets zero. Then we need to wait for the recombination of the charge carriers in the BJT before the device turns off. As a result, we will observe the tailing current in IGBTs at the turn-off moment. Another drawback of the IGBT is that the MOSFET must tolerate the same blocking voltage as what the BJT does. By taking the base current passing through the MOSFET into account, we soon notice that the MOSFET occupies a large space on the die despite the fact that it handles around 1/10 of the total current. This implies that in low to mid-range power conversion applications, we cannot achieve a satisfactory volume density. However, for high power applications, we definitely can achieve a better volume density than what power MOSFETs can offer. To get a better understanding of the IGBT, let's take a look at the IV characteristic of a 20 ampere 600 volt sample IGBT. Of course, for a gate voltage of 0, there is no current conductivity from the collector to the emitter. However, by giving the gate some positive voltage, the IGBT turns on and conducts. For small gate voltages such as 9 volts or 11 volts, the IGBT gets saturated soon at a certain collector current. However, by providing the IGBT gate with a proper large voltage such as 15 volt, the device turns on fully and the current saturation happens at a much larger current, which we cannot even see in this graph. So by assuming that I am giving 15 volt to the IGBT gate at 20 ampere, the voltage drop over the IGBT under discussion is 2 volts. But wait a second. A voltage drop of 2 volt is too much for a 20 ampere device. Of course, we can find a 20 ampere 600 volt MOSFET that has a much smaller voltage drop. This is why in low to mid voltage and current applications, we are more interested to use MOSFETs, and in large voltage and current applications, the tendency is to employ IGBTs. Let's compare the IGBT I-V characteristic with that of a BJT. We already saw the I-V diagram of the 20 ampere 600 volt IGBT when the gate voltage is 15 volts. To turn on a BJT, we need to give the BJT some base current. For this BJT, I am giving the BJT base a current of 2.5 ampere. As you can see, this BJT does not even reach 20 ampere, although its base current is 2.5 amps. For any collector current below 14 ampere, the BJT has a forward voltage drop smaller than that of the IGBT. However, for a current greater than 14 ampere, the IGBT provides a smaller voltage drop. In this lecture, I discussed a brief history of IGBT, differences between IGBT, MOSFET, and BJT, IGBT semiconductor structure, IGBT circuit model, and the IGBT I-V characteristics. In the next lecture, I will wrap up this course by discussing the JFET. Thanks for joining this lecture of Peacademia.